Another interesting device is the one that produces, well, the one called the diffraction grating. And so, and in this case, instead of having just two openings, two slit, like the double slit, we are going to have many of them. We are going to have n, and they are going to be closely spaced. So now when we shine light through a device like this, then we are going to get diffraction again, but we are going to get a little different pattern. So this is called a diffraction grating, and the bright fringes, again, they are going to happen at angles such that the sine of theta m is equal to m lambda. Again, and the positions of the maximums then have this equation, which is similar to what we had before. So now this is the picture that we have. We have light coming here, right? This could be a laser. And then we have many openings. This is your diffraction grating. And then light is going to come out of these openings, right? And it's going to travel towards the screen. This is your top view. And then what's going to happen is here you have your grating, your light coming, and then what's going to happen is you want to locate the maximums, you want to locate the bright spots along this screen here. And the positions of these spots are going to be given by, again, a similar equation to that of the double slit. And so that gives you this equation for the position of the diffraction grade, the maximum. So here's what it looks like, and you're going to see that in a way these maximums are kind of narrower than the ones you had for the double slit. And this m is called the order of the diffraction, and the amplitude, the wave amplitude at the points of constructive interference is n times a, where n is the number of slits, and then because the intensity depends on the square of the amplitude, the intensity of the bright then is n squared times the intensity of one opening. So with this, then we can use this to find things like the wavelength of light. Okay, if we want to find the wavelength of light, then we can use a diffraction grating and apply the equations that we know. Another important one is the single slit diffraction, and this basically, using this, you can get a condition for when to switch from wave optics to ray optics. So a single slit is just one opening, and so there's no, so the way to understand why you get diffraction here is to use Huygens principle, in which he claims that at each point, if this is a plane wave, at each point becomes like a secondary source, is generating waves. And those waves are going to interfere far away from each other. So this is your picture here. You have your opening, right? And then each point is generating a secondary wave. And you can see here, then you're going to get the interference patterns right here. And therefore, you're going to get your diffraction patterns. So if you have in this situation in which all the waves are going straight, then you would have a central maximum, and that's all you're going to get. But if you have but if you want to look at an angle, okay, and then you're going to have fringes again. And the shape of the intensity in the screen is going to be like this, where you have a sharp maximum and these smaller maximums here, and then you have these dark spots. The location of these dark fringes, these points and this point, occurs at P lambda over A, where P is 1, 2, 3 is a number, and A is the width of the aperture here. So the central maximum of this single slit diffraction pattern is much brighter than the secondary one. So you can see here This is way much brighter than the other ones. In this picture, we have the diffraction pattern for a single slit, and the width of this central maximum uh, is given by this equation here, right? This is the width and depends on the length, the distance to the screen, the wavelength, and uh, the width of the aperture. So the farther away from the screen, the wider the pattern lights become, the narrower the opening, the wider the pattern of light becomes. So what this is, so we can use this then to have a condition on when to use wave or ray models, right? And so basically the idea is that uh, if you get diffraction patterns, then you should use a wave model to describe your system. And if the diffraction is negligible, then you can be safe using a ray model to describe your system. So the condition that basically would give you that is this condition here. And so for visible light around 500 nanometers, then a distance of 1 meter and an aperture of 1 millimeter would be the threshold and from which you have to switch from wave to ray models or back or or the other way. Okay, thank you very much.